Hello. This video we will be going over learning objective 3, which was using a molecular orbital theory to explain how pi bonds and heteroatom substituents affect carbocation stability. So first of all, we're doing this because in the SN1 reaction, we form a carbocation. We also have learned that it plays a big role in SN1 reactions, and the stability of this carbocation is influenced by nearby atoms and structural features of the molecules. So, how can we explain this? Well, we can just use the molecular orbital theory because it can help explain the interactions between the atoms and explain why the certain carbocations are more stable than others. There are two factors that can lead to this. First of all, I'm going to explain the pi bond delocalization, and secondly, I'm going to explain the heteroatom substituents. So, first of all, first scenario is when a pi bond is adjacent to a carbocation, we have an empty p orbital on the carbocation. So, this empty p orbital overlaps with the pi bond, making it more stable. Why? Why is this the case? It's because this overlap creates delocalized molecular orbitals. They're kind of just going around, allowing this positive charge to be more evenly dispersed through resonance. So, as a result of this, we can see that the carbocations that have a conjugated system are way more stable than the ones that don't, or not even conjugated. Just whenever there is a pi bond next to it, you can see that the stability is much higher. Second of all, let's talk about the heteroatom substituents. So, we can talk about oxygen and nitrogen since they're very commonly seen. So, whenever these atoms are connected to the carbocation. So let's say that we had a carbonyl and then left, and then we have a carbocation there. These molecules, the oxygen or the nitrogen, they have lone pairs. And these lone pairs act in a similar way as the pi bonds did. They overlap, stabilizing the carbocation because the charge is more evenly dispersed through resonance. Because the interaction forms the partial bonding in new molecular orbitals. This leads to a much increased stability of the carbocation. The lone pairs can also help spread the positive charge and lower the overall energy of the system. How come? Well, that's because it is more dispersed, it becomes more stable, and the more stable something is, the less energy it has. And then whenever the heteroatom is directly next to the positively charged atom, that helps stabilize it even more. So it just depends on how close it is. But in general, we can conclude that the empty p orbitals can overlap and create a more stable environment for the carbocation. And the the heteroatoms, the lone pairs act in a similar way. They help the charge spread and disperse more evenly. Therefore, we get a more stable carbocation. This is why it is so important in SN1 to be a tertiary because it is able to be more stabilized, whereas a primary carbocation is not very stable whatsoever.